Welcome to a section on fundamentals of generative AI and model architecture. In this section, we're going to cover our first module, which is deep dive into generative models. In this module, the first generative model that we will look at is variational autoencoders or VAE. In here, we'll talk about variational and autoencoders as understood by a 10-year-old. Then we'll look at variational autoencoders basics, and then we'll do a deep dive into variational autoencoders. So let's get started. Variational autoencoders as understood by a 10-year-old. Imagine you have a big set of Lego blocks, and every time you build a new creation like a car, a house, or a spaceship, you like to remember it. But you don't want to write down every single Lego piece you used. Instead, you just jot down some notes about the shape, color, and size of each thing you made. With these notes, you'll be able to rebuild something that looks very similar or even make something new. A variational autoencoder VAE is a bit like this idea of remembering and rebuilding with just some simple notes. How does a VAE work? Encoding, making notes, the encoder. When you build something, the encoder looks at your creation and takes just enough notes to remember the main feature. It might jot down that it's mostly blue, it has wheels, or that it's tall. These nodes go into a secret code place called the latent space, which is like a storage room for your summaries of each creation. Next, we have decoding or rebuilding from the nodes, which is also called the decoder. Now, if you ever want to rebuild one of your creations, the decoder reads the nodes and rebuilds something that looks pretty close to the original. It's not exactly the same, but it's similar enough that you recognize it. Next is creating new things from mixed nodes. Here's the fun part. You can't mix up different nodes from different creations to make something new that combines parts of each. You might mix nodes from your car and spaceship to create a flying car, for example. The VAE can do this because it has learned how to blend nodes together to come up with cool new ideas that still make sense. And finally, why are VAEs so useful? With VAEs, we can learn to recreate things like images with just a little bit of memory space. This helps us make similar new things based on what we have already learned, like creating new faces, cartoon characters, or game levels based on ones we have seen before. So, VAE is like having a super smart notebook where you can store simplified memories of your favorite Lego builds, then use those notes to create cool new designs over and over. I hope you were able to understand the basic crux of variational autoencoders through this explanation. If not, we're just going to jump into variational autoencoders basics. Now, variational autoencoders or VAEs are a type of generative model in deep learning that can learn the underlying patterns in data and generate new similar data points. Introduced in 2013 by Kinma and Welling, VAEs are particularly useful for generating images, text, and other complex data types. Here's a breakdown of their key concepts. First, architecture overview. VAEs consist of two main parts, an encoder and a decoder. The encoder maps input data, example an image, into a lower dimensional latent space which represents the data's compressed version. The decoder takes a sample from this latent space and reconstructs the original data, aiming to closely match the input. Next, let's look at latent space and sampling. In standard autoencoders, the latent space is a direct encoding of the input, but in VAEs, it represents a probability distribution. Instead of encoding inputs into a fixed point, VAEs encode them as a distribution, usually Gaussian, defined by a mean and a variance. During training, VAEs sample from this latent space to generate outputs, introducing variability and allowing for more diverse generated data. Loss function reconstruction plus KL divergence. The VAE loss combines two components. First one is the reconstruction loss, which measures how close the generated output is to the original input. And we have KL divergence, which ensures that the latent space distributed is close to a normal distribution, promoting smooth transitions between points in the latent space and improving generalization. This balance in the loss function is key to learning meaningful latent representations. Let's look at the applications. We have image generation. VAs can generate realistic variations of images like faces and landscapes. Data imputation. VAs can handle missing data, filling gaps in data sets by sampling likely values. Anomaly detection. By learning the normal data distribution, VAEs can detect outliers or anomalies. Semi-supervised learning. VAEs have been extended to improve classification tasks by incorporating both labeled and unlabeled data. Let's look at some strengths and limitations. Strengths: VAEs learn disentangled representations, which makes them powerful for interpolation, where new data points are smoothly generated between existing data samples. The limitations are compared to other generative models like GANs, VAEs can produce slightly blurry images because of their probabilistic nature and the use of Gaussian prior. Extensions: we have conditional VAEs or CVAE, a variant that conditions the generation process on additional information, useful for generating specific types of data, example, images with particular attributes. We also have beta-VAE, adjust the KL divergence terms weight to control the amount of disentanglement in the latent space, useful in cases where interpretability of the latent dimensions is critical. VAEs are a powerful framework for generating tasks, offering a probabilistic approach to understanding and generating complex data distributions. Next, let's dive deep into variational autoencoders. So, diving deeper into variational autoencoders, we'll explore how they work at a mathematical level, why they are structured the way they are, and their unique characteristics that make them distinct from other generative models. First, let's look at the mathematical foundation. A VAE is built upon Bayesian inference framework that uses probabilistic graphical models. The goal is to approximate the complex data distribution Px, example is distribution of images, through a latent variable model. In this particular model, X represents the observed data, example an image, and Z represents the latent variables, hidden factors that generate the data for this case. VAs assume that the data X is generated by some latent variable Z via a probabilistic process, meaning they aim to learn the conditional distribution P of X by Z and the prior distribution of latent variables P of Z. Next, let's look at some key components of VAE. We have the encoder, which is recognition model represented by Q of Z by X, which maps the input data X into a latent variable distribution Z, usually Gaussian. This model is parameterized by a neural network and produces the mean, mu, and variance sigma square on the latent distribution. Decoder, generative model P of X by Z, reconstructs data X from a sampled Z. This network aims to maximize the likelihood of generating data points similar to the input data. Unlike standard autoencoders, which encode data directly into a fixed latent space, VAEs map input data into a distribution from which samples are drawn. Next is our objective is evidence lower bound or ELBO. The VAE optimization objective is to maximize the evidence lower bound, which is derived from the marginal likelihood of the observed data P of X. The ELBO can be expressed as ELBO is equal to E of Q Z x log of P of x of z minus KL is Q of z of x or P of z, where the reconstruction term E of Q of z of x log of P of x z, the first part, measures how well the reconstructed data matches the input. The second part, KL divergence term KL Q of z of x or P of z, ensures that the learned latent space distribution Q of z of x is close to a prior distribution P of z, typically Gaussian. This promotes a well structured and smooth latent space. Let's look at the reparameterization trick. A crucial technique in VAEs, the reparameterization trick, allows backpropagation through the sampling operation, enabling gradient based optimization. The trick involves rewriting the sampling step from z tilde q of z of x to z equal to mu plus sigma times epsilon, where epsilon is n of 0 to 1. This makes the operation differentiable, allowing gradients to flow from the loss function through the encoder and enabling efficient training with standard stochastic gradient descent. Let's look at the latent space and generative process. VAEs generate data by sampling from a continuous latent space, which enables them to produce novel variations of the input data. The latent space structure, where the KL divergence term pushes the latent variable z to follow a normal distribution, resulting in a well organized latent space where similar points correspond to similar data. We also have interpolation, which is a structured latent space allows smooth interpolation between points, enabling the generation of new data by interpolating between existing samples in the latent space. Training VAEs. The training process involves minimizing the ELBO to balance two competing goals: data reconstruction, which ensuring that the generated data resembles the input data, and latent regularization, which encourages the latent space to follow a normal distribution, which makes it easy to sample from and reconstruct diverse data. A typical VAE architecture is trained using a loss function that combines reconstruction and KL divergent terms, usually balanced by a weighting hyperparameter to tune the level of regularization. Let's look at some of the challenges in VAE training. We have blurriness in generating images. The probabilistic nature of VAEs can sometimes lead to blurred outputs, especially for high dimensional image data. We have KL vanishing. If the KL divergence term dominates, the encoder may ignore the latent space, leading to a collapsed latent space. Techniques like beta-VAE adjust the weight of the KL term to encourage learning of more useful latent variables. Let's look at the extension of VAEs. We have conditional VAEs or CVAE. This variant conditions the model on auxiliary information like labels, enabling more controlled generation. For example, a CVAE can generate specific types of images by conditioning on class labels. Beta VAE introduces a hyperparameter beta to weigh the KL term, encouraging disentanglement in the latent space. This is useful for applications where interpretability of the latent dimensions is essential. Then we have VQ-VAE, which is vector quantized VAE. Instead of using continuous latent variables, VQ-VAE uses discrete latent codes, making it more suitable for tasks requiring discrete representations, example text or speech generation. Next, let's look at the applications of VAEs. We have image generation and interpolation. VAEs are popular for image generation tasks as they can smoothly interpolate between different images, creating new visuals. We have anomaly detection. VAEs can learn the distribution of normal data, making them effective at identifying anomalies by spotting data points that deviate from this learned distribution. We have semi-supervised learning. VAEs can be extended to leverage unlabeled data effectively, improving performance on supervised tasks with limited label data. And we have data imputation. VAEs can be used to fill in missing data by sampling likely values from the learned distribution. Finally, let's look at comparison with GANs. Now, unlike generative adversarial networks, GANs, which are adversarial models with separate generator and discriminator networks, VAEs are probabilistic models that rely on a single encoder-decoder architectures. We're going to look at GANs next, but for now, let's do the comparison. We also have what are the advantages of VAEs? VAEs have an organized latent space that supports interpolation and are easier to train than GANs. Limitations: VAEs often produce blurrier images than GANs due to Gaussian assumption in the latent space, whereas GANs generally generate sharper and more realistic images. So, just to summarize, variational autoencoders offer a unique approach to generative modeling by combining deep learning with probabilistic inference. They are valued for their ability to learn structured latent spaces, enable data interpolation, and perform generative tasks effectively.